So often with calculus, you're going to have some function. You're going to be working with some function I'm going to tell you, and it's all going to be about how fast this thing is moving. Okay, now there's two types of rates we're going to find. One is the average, which you know how to find average. The other one's going to be instantaneous speed, which is going to be more of the calculus stuff. And you can see that H I mentioned earlier, you're going to have a lot of H's and things like that in these problems today. And that just means very, very, very small number. Just think about that. It's a very, very small number. That's all it is. But first, let's just start with basic. How would you graph this? This was back in Algebra 1, right? That's all we're going to do. We're going to start from the very, very, very beginning. So if you had some function, like f of t, the function of time, that's what t stands for. You can put that in there. Think of t as time. Ew, that's not working. There we go. There we go. And time is in seconds. A lot of stuff in calculus is all word problems. That's why you have to understand what you're doing, not just get an answer, because it's a word problem. It solves a real life problem, more than likely. And then we got, this is going to be in feet. So it says that our y, or our function, is going to be in feet. Okay. So if we're going to graph this, basically at no seconds before we even start, well, how far has this traveled after no time has passed? So it's logically, what would be the answer here? Well, no time has passed, and the thing hasn't moved, right? So that should make sense why it's at 0, 0. Again, we want to understand what's going on, not just, oh, I got numbers and I can plot them and get a graph, and look, I got a graph, I'm done. But understand what's going on here. After 1 second, how far has this object traveled, right? So it's the same as plugging it in. And recall that when you do an order of operations, you have to do the, what's it called? You have to do the exponents first. So you're always doing that part, squaring or to the third power or whatever it is. And then lastly, you multiply by what's in front. So in other words, you don't do these from left to right. You don't go 3 times 1 and square. It's order of operations all the way every time. So we just get 1 squared times 3, which is just 3. And then we repeat with 2 squared. 2 squared is 4. 4 times 3 is 12. And then one more time. Right? And this is what you did back in, like I said, Algebra 1 or maybe in 8th grade. Whenever you took algebra or did this kind of problem. Just make a t-chart, more or less. 3 squared is 9. 9 times 3 is 27. Right? And often you'll have to graph these, and you'll have to loosely graph these, meaning it's just going to be a blank axis. So just remember, for like numbering your axes, you always look at, like here it starts at 0, goes to 3. So you want to use most of the axis when possible. So let's just say like this is 3 right here, and you want to evenly space 1 and 2. All right, so you could say this is 1, this is 2. Just make sure these are approximately equal widths. They don't have to be precise, exact, but you want it to be, as accurate as possible. Same thing with the function axis, or y-axis. You notice that these will be labeled as f of t and t instead of x and y, just because we're solving real-life problems that have time and feet and things like that. And you see the biggest number is 27, so you don't want to make the highest number 27. Usually you round it off and say, well, that's 30. Make that the height. That way when we're graphing, we know we're not going to graph this and it's going to go off our graph because we made our numbers too small. And the proper way to do this is now find the halfway point of 30 and 0. Approximate that. And that's 15. And then you can estimate the other tick marks in between these. So we got a 20 and a 25, right? And we got a 5 and a 10. And that way you have a graph that more or less it's evenly spaced out, and it's going to give you some an accurate graph. Later on calculus, you'll have possibly a graphing calculator, so that'll be working for you as well. And then you just go through and plot. So of course, after this thing hasn't left the garage yet, so it has not moved any distance, so that's why it's at 0, 0. And then after 1 second, it has moved 3, so you have to estimate 3. And then it's an estimation. This is 5, so you kind of find the midpoint, right? Somewhere around there. And then 2 seconds would be 12. So we could find 12, a little bit above 10, roll over to 2. All right, nothing we haven't done before. And then, of course, it jumps way up to 27. Go way up here at 27, that's going to be 3. And this is a continuous graph, so we connect them all up. Often, everything you're going to be working with is going to be quadratics, which means it's to the second power, which means, you know, it has a general shape of a parabola. Sometimes it's going up. Often it's going to be going down. It's going to be a negative, and it's going to be a parabola looking like this, which resembles an object going up in the air and then falling. So you'll see a lot of negative 10t squared, a lot of negative, some number negative in the front. That just means it's going up in the air and coming back down. But we deal with a lot of parabolas at first, and then we get it to the higher stuff afterwards, right? All right, and if we're going to describe this thing and how fast it's moving, we are talking about rate. And we know that distance is rate times time. You know that from all your background knowledge and whatnot. And if we're going to solve for rate, or solve for r, divide both sides by t to get r by itself, we have rate is distance over time. All right? And you guys know this from, like, I don't know, just driving the car. You notice that it's always like miles per hour. When you say how fast are you going, that's a rate. So when you think of, you know, rate, you see r's all over the place. Think about velocity, speed, how fast you're going, just going in the car, or even walking, or how fast something is moving. We're talking about rate, right? And another fancy word for rate is speed. But really, I want you to think about this in the context you already know, which is slope. So anytime you see rate, think slope. You're calculating the slope of a line, nothing more than that. So a lot of the work we're about to do just looks like you're finding slope, but it's no longer just slope. It's, you know, calculus is where you bring all that math you've learned so far and you actually solve real life problems. It's usually about how fast something's growing, falling, how fast it's going, you know, exit velocity to, you know, get out of Earth's gravity or whatnot. Like, it's all about speeds, right? So how fast it's going. So just think, when you see rates, just think about slope. That's all we need to know. Okay? How we write everything is a little bit different. So you see right here, that little triangle, that's delta. That's a Greek letter. That's actually, if you write out the Greek letters, you know, alpha, beta, gamma, I think it is, and then delta. Right? So delta is actually, you know, the triangle is actually the letter D. You want to think about it, right? So that just means a change, right? So every time you see this little triangle, it just means how much is it changing or moving, right? Or, yeah, same thing here. So if we know how much the distance is changing, how much this time is changing, that's basically what slope is, right? So when we did slope back in the day, we wrote it as y2 minus y1 over x2 minus x1. We could write that as the change of y's over, or delta y over delta x. These mean the exact same thing. So don't let this little symbol fool you. This is a lazy way of not having to write out this y2 minus y1. So anytime you see this delta over delta, it just means you're finding the distance, which means you're subtracting. Finding slope, okay? Just finding slope. So that's all we're really going to do. But yes, you're going to get an answer. More important, know what the answer means in the context of this problem. And I think every single one of the problems uses the 3t squared. So it's not that every problem in calculus uses 3t squared. It's going to be repetitive today. So it's going to change, of course, with future assignments and on your homework. It's not going to be 3t squared. But we're just trying to keep it simple so you don't, so you can follow along. So if we want to find, let's see, the average speed, remember, average speed, just think of finding slope, right? Average speed is finding slope. Rate of change, you know, when you see these in the directions, you're like, what, average speed and rate of change? Just find the slope, right? Now, usually with the slope, you need 2 points, right? That's how you find slope. So if you go up here and say, if you have a graph of it, so t equals 0 and t equals 2, you can just go up here and see, well, here's t equals 0, here's t equals 2, and think of drawing a line between them, and what you're doing is just find the slope of this line. Okay, that's your assignment. It's really just to find the slope of that line. So it'll give you 2 times. You have to have 2 points to find a slope, right? So if you can do that, you're already doing calculus, right? That's all. That's how we're going to start this. Okay? So find the slope of that line. Now we're going to write things out a certain way, so you're writing calculus ease. So it's important to write this way because you guys are going to be AP tested on this. And if you just decide like, well, I know how to get the number, I'm going to leave all the other stuff off, I don't like it, just expect to get 1s and 0s on those problems because they want you to write it like an essay using the proper language, grammar, but in math, right? So you do need to write all the stuff I'm about to show you, even though it's very basic. So we got delta D, delta distance, the change of the distance over the change of time. Right? It's going to be f of 2 minus f of 0. Okay. Now this is the same as y2 minus y1. Okay. But we use function notation mostly. We don't use a lot of y's, and for a very good reason. As we get into that, you'll find out. And that's why on the IXL I had you practice a lot of function notation because you really have to know that inside and out when you're doing this. Right? But if you don't like, where's this? Just think of it as y. We're just going to plug in f of 2, which is right here, which is 12. Right? So it's just y. Well, what's the y value? We got 2 and 12, and then 0 and 0. So you just find the slope between 0, 0, and 2 and 2, 12. Okay. But how we write it is just a little bit different. Okay. And then we'll say 2 minus. So that's just 12 minus 0 over 2 minus 0, which of course just equals 6. And very important, calculus, there's a lot of word problems. Most of it's word problems. You have to have units on your answers. So if your question has like, seconds and things like that, and feet, make sure your answers have those units as well. So we have feet per second. Distance over time, right? So feet per second. Okay. And all that says is that on the average, going from the very beginning, from the start, after 2 seconds, we went an average of 6 feet per second. After 1 second, it was at 6. After 2 seconds, we're at 12, which makes sense. Right? We had 2, 12. So after we've gone, we haven't moved at all at 0. We've gone 6 feet after 1 second. We've gone 12 feet after 2 seconds. Okay? That's all that means. But that's important to understand what we're doing, even if it's basic. Okay? So do the same thing, but right now do from 2 seconds to 3 seconds. So instead of using 0, 0, use 2, 12, and the 3, 27. Question?
Is calculus a part of physics or is physics a part of calculus?
Without calculus, you can't do the physics. Yeah. Without physics, there's no need for calculus. They're kind of codependent. They need one another. They justify their existence. Good question. Let's see here. All right. So you can try it on your own. I'm going to do it up here as well. But just remember, you're just finding the rate of change, which is the same as the slope. So change of distance over the change of time. And some of you might be tempted already, after me telling you not to do that, to not write this part. Write this part. Right? Make this part of your work that you show. Okay? Not doing something that's less than I don't need that because I can get the answer. Again, if you get stuck on the I know what the number is, you're going to miss the point of the whole thing. So write it out. Once we start putting more complicated things in these parentheses, this format, this simple basic format, really helps you start problems and set things up nicely. Okay, so all good reasons for doing the right things here. Even though if we're just finding slope. Alright, so what's wrong with my answer? Alright, so let's, after everything, oh yeah, I got the number. Okay, well, don't forget units. When it's a word problem. Not all of them are word problems. Not all of them say, like, here's a particle or here's a object in the, in the sky that's falling. But when they do have those, the answer should have units. Okay? So basically, we've looked at slope again, and instead of calling it slope now, we're going to call it rate of change or average speed. Okay? So that's important to retain and recall so that when you're reading the directions of your homework, when it says find this and find that, you know what the directions mean, and they know what you want them to do, which for some people is the hardest part. Like I know what we just did. We did about examples, and they read the first direction, or they look at the first problem, they're like, I don't know what to do. They read the directions, like, well, I don't know what that means. So, take note, just like you take a note of the math, take note of how to dissect the directions so you know what to do when you get the problem. Yep.
Our answer is an estimate because, or is it because of if you just make a straight line rather than directly on that?
It's an estimate? What do you mean?
Is it an estimate because we're taking a straight line in between the points, but we're not taking the actual curve of it. If it was the actual curve, would it be more accurate, or is the line more accurate?
Yeah, well, stay tuned. You're about to find out. So, as Michael pointed out, we have this, we're finding the rate of change, but it's not quite, I don't know how you say, it's not taking into account how this is curved, right? And the video mentioned that I showed you says, well, things are moving at different speeds along there. So this object could be moving faster here, it's going to be then here, and it could be a little faster here, a little faster here. And our next question is to find out, well, how fast is it exactly moving at 2? Right? So if we want to find the speed or the velocity of how fast something's traveling exactly at 2, how do we do that? Because the only mechanism we have to find speed or rate is slope, and slope requires 2 points. So how do I find the exact speed at 2, like this would be 2, 12, if I only have 1 point? If I don't only have 1 point, how do I do this? So this is where calculus kind of begins. We call this instantaneous speed. So now we have two different vocab here. We have average speed and we have instantaneous speed, and you need to know the difference between those. Right? So the directions are very clear. If it says find average, you got to do this kind of work. If it says instantaneous, you got to do this. So what this means is, well, if we want to find how fast something's going, let's say in this problem, exactly at 1 second, right? Not an average from 0 to 1 and from 0 to 2 or whatever, but exactly at 1 second. That's where we introduce this concept of, well, let's look at something. Let's say I zoomed in very, 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 very close to right here, and I picked a point that's like basically right next to it. So close it's right next to it, it's not even visible. If I was to graph it right here, you couldn't even see the distance between them because it's so close. Meaning like H is like point, imagine like I want to pick, 1, 3, right? And then my 1 plus H, think of it as like the other point that we're going to use in our formula is going to be like 1.0000000, maybe a million zeros and then 1. Like, we still have 2 points, but they're so close to each other that it looks like the same point, but now we can use the slope formula and find how fast something's moving at exactly that point, right? And there's no longer going to be an average over like 0 to 2 seconds, but it's going to look at exactly what's going on at 1 or 2 or 3, okay? And we want to make this thing as small as possible. So this H, what we do is we make this approach 0. We want to get that H as close to 0 as possible, but never equal to 0. And this is where limits are going to come back in. So all your questions with instantaneous speed have limits involved. And we did a whole chapter on finding limits, and you're going to use all of that. Everything, right? So here's how we do it. So we're going to set it up this way. Average speed for instantaneous is going to be, we're going to write this formula, but instead of just having a number 2 and 0, I have my values are going to be 1 and 1 plus h. All right, so I have f of 1 plus h minus f of 1. And for those that did the IXL, this is why I assigned this IXL, practicing plugging in expressions into equations. So you know how to do this really well, square them, and do all the work that's necessary. If not, you'll get the practice by Friday. On the bottom, we're just subtracting 1 plus h minus 1. This is still just slope. This is still, just think of it as y2 minus y1 over x2 minus y1. It's just what we're plugging in is a little different. So we got 1, and then we got the number just a little bit bigger than 1. Tiny, infinitesimal, tiny, little as possible, a little bit bigger. And now our function is still the one from above. So we're still working with this f of t is 3t squared. So I need to take this right here, 1 plus h. What this means is take 1 plus h and you substitute that in for t. All right, so what does that equal? That would equal 3, 1 plus h squared. So you see how I just took this 1 plus h, substituted in for t, so the 3 is still there, the squared's still there, right? And now there's a 1 plus h instead of the t. All right, and same thing here. And so we'll go 3, and substitute in 1 for t. So it's just 3 times 1 squared, 3 times 1 squared. And on the bottom, this usually simplifies on the bottom, not usually, always simplifies when we're doing these types of problems. The beginning right here, this one will cancel out with this one. So we have 1 plus h minus 1, so we just end up with h. And do some algebra. And recall what I said earlier, when you're plugging things in, you do the exponents first, then you multiply by the number in front. Same thing here, does not change. So we need to square this, right? We need to do 1 plus h squared. So if you're, go ahead and do that real fast. What is 1 plus h squared? What do you get? And write that in the parentheses. What's 1 plus h squared? Got your answer? All right. Now, if you have 1 plus h squared, you need to pay attention real fast. This is the wrong answer. So you cannot distribute. If you're just like, oh, I'll just go like that and go like that, that has never existed in the history of mathematics. You made it up yourself. Don't do it. Okay? So what we're doing here is 1 plus h times 1 plus h. Or some of you like that box method, but what happens is you get 1 squared plus 2h plus h squared. Right, so you have to, and this is just basic algebra 1. So often we have people that mess up on this stuff and get stuck. So that's, again, this is why we did this on the IXL, so you had practice before today. And now we could distribute. Now you can distribute in that 3 to each one of these, right? So I'm going to roll on back over here and continue. So we'll have 3 times 1 squared is 3, all right, plus 3 times 2h, 6h, 3 times h squared plus h squared, 3h squared. And then we got the minus 3 here on the back end hanging out. Still all over h. And kind of like the beginning over here, the blue, we have these ones cancel out, right? That happens on the top now. The top, the first term, and the last term will cancel each other out, equal 0. So now, good news, we're left with everything h. So after all of that, you should, by this point in every problem, have only h's left over. That's how you know, kind of check in, all right, we're in the right place, right? Because I don't have any other numbers floating around, really. It's okay if you do, but often they'll just all cancel out at the beginning. Then we can see, okay, how to simplify this whole expression. Okay, we got h everywhere, so let's factor out an h. From 6h and 3h squared, just factor out GCF of h. Again, more algebra 1. It's all over h. And once again, now we can cancel. Every now and then, not so much at this point, somebody would do like something like this. You know, obviously that's just like the exponent thing. You made that up. That's never existed in the history of math. Don't do that. You can only cancel out factors, things that are being multiplied. So see how 6h plus 3? That's your signal that this can't cancel with anything top and bottom. Right? So it has to be a product, right? Some sort of factor. Then it cancels. All right, so in the end, this whole thing just equals 6 plus 3h. All right. So, a lot of algebra just to, get us used to it all. But what does this mean? 6 plus 3h. What is this h? Recall, what does h mean? H is a very, 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 very small number. So what we're going to do at this point, right, and it says here, these things are so close together, closer and closer together, so close that they basically become the same. So we're going to say, well, what if h is almost 0 but not quite? We are going to take the limit. And that's what makes them as close as physically, abstractly possible. And that's what makes us instantaneous, right? It's that fast. The points that we're using for our slope are so close together. So what we're going to do is take the limit as h goes to 0, approaches 0, of the 6 plus 3h. And you recognize this is just like a straight line type of thing, so you might recall that all you need to do in this situation, because when you plug in h, you're not going to end up dividing by 0 and getting undefined or any of those rules like asymptotes or anything like that. This is a very straightforward limit. So really all you need to do when you're taking the limit is you're going to substitute in whatever this value is for h. In this case, you just get 6. So the instantaneous speed at 1 second is 6 feet per second. And the concept of what I just did is way more important than 6. So what's important is that you understand that what we did is that we picked a point 2, and we picked a very, very, very close point to it, and we just found the slope of them. That's what we just did all here. That's what all that h and all this stuff, it's just finding the slope of 2 points that are infinitely close to each other. Because we can't find slope of just 1 point. We have to have 2. So the best way to find what's happening immediately right now is pick the 2 points that are the closest possible to each other that could physically be. And that was accomplished using a limit. So the function will change. Again, on your homework, it'll change what it is. All of them are 3t to the second, so you'll see, like this number might change. It might be to the third power on different problems. Just how you, evaluate these functions and plug things in, what you're practicing. I highly recommend, well, I'll show you on the next thing here. So let's flip it over and do one more. I'll do one more without less talking. If you want to go ahead and try it on your own and just follow along, you can. If you want to just, see one more completely worked out, you can do that too. So for these, what we're going to do, for all these problems, it has to give you the function. If you're going to find the instantaneous rate of change, you have to be given the function and at what time. Notice if it's average, you're giving 2 times. So you kind of can tell by reading the directions. They give you t equals 0, t equals 2. You know they're talking about average. If they say, well, just right here, it's still 2 points, but one of them is h, plus h. That's the other one. So what we're going to do from here on out is that we're going to include the limit, this part, throughout the whole problem. Okay, throughout the whole problem. So we're going to start off, when you see instantaneous rate of speed, or rate of change, you have to include the limit from the very beginning. So we're going to say, well, if I want to take the instantaneous, I only have 1 point. This limit as h go to 0 gives me the other point I need to find a slope of a line or rate of change of something moving. Okay? And it's going to start off with f of 3 plus h. Right? This is the y coordinate that's just a little bit bigger than f of 3. And I want to find out how far apart these are from each other. Remember, distance is different. So the reason why we're subtracting is because this will tell me how far apart these are from each other. Right? And that's where the change in d comes from. And on the bottom, very similar. Right? My x's, x2 minus x1. So if you're given just one of them, you want to think of it, well, that's like the x1, which means your x2 is just a little bit bigger than that, right? H is that tiny, tiny number. This is just a little bit bigger, and that's why it's listed first, because we're doing technically this is the bigger number compared to both of them. So when we subtract them, we get a positive number. And then we say equals. I highly recommend, I know some of you like doing like this horizontally. I highly recommend from this point out in your rest of your life, stacking things vertically. For reasons will make a lot more sense later on. It's easier to see a flow of the problem. It's easy to see your work, to find mistakes. So I highly recommend it moving forward, stack things vertically. And then we'll plug everything in. So I'm going to take, once again, I'm taking whatever's in the parentheses, substitute that in for the variable. Just the variable. I can't keep it. There we go. Just that variable. That's where it's going in. So I have the 3, then something to the second power, right? Back here. 3 plus h, second power, minus 3 times 3, second power. All over, once again. The bottom, 3, positive 3 plus h minus 3 h. So you should always expect this bottom just to turn into h. Equal sign, rewrite limit as h goes to 0. And just continue to do the same thing we did on the front. Right? We're just going to go through, expand it, know how to expand it correctly, distribute the 3, cancel things out, factor out an h, and see what's left over. And then at the very end, take the limit of what's left over, and that'll give us our final number, our final rate of change at 2 or 3. Yeah. It's not necessarily showing any work. You don't, at this point, when you get the calculus, like 3 plus h squared, most of you, I know this from looking at your work, you can just do this in your head, and you just say, oh, that's 9 plus 6h plus h squared. So there's no necessary to, if you're still showing work and writing boxes like you're in Algebra 1, you don't have to do that. If you need to, of course, do it to get the right answer, but at some point, it's like training wheels. You're like, okay, I don't need that anymore. I'm going to stop using that and just be able to do it, really quick with no side work. Okay. All right, keep on going down. Got 27 plus we got 18h, 3h squared minus 27. So once again, we have those. The front and back are canceling. We have that here. On the bottom at the very beginning, and then usually on the top towards the end, you'll see these cancellations happening. So if it does it, maybe something's off. Like a little red flag if you don't see that. Do a little factoring. And these equations will change. If we're doing something other than parabolas, it's not going to work out entirely the same way. But for now, it will. Once you have everything simplified as much as possible, that's when you actually take the limit. So that's when you substitute in the value, which is going to be 0 for all of these, into here, so you just get an answer of 18. Now, if you want to, you could write, well, let me show the substitution of 0 for h, or you could just say, Well, I get it. 18 plus 0 is just 18 and 18. And, of course, units. Okay. And this should make sense. Compared to what we just did up here, we found the average rate of change from 2 to 3. All right, so we basically found the slope of this line from 2 to 3. And it makes sense if I'm looking at just at 3 only. Well, if I look at just 3 only, well, that's a steeper line, so I expected my answer to be bigger. This slope came out to 15 feet per second, and what we just did came out to 18 feet per second. So when you get an answer and you have a graph, it should make sense. Again, go back and actually ask yourself, does that answer make sense? Why does that work? You could have predicted at the very beginning, before we did the problem, that, okay, this is 15. This looks like it's going faster. It looks like it's steeper at that point, so I better get a bigger number than 15 after I finish this problem. So that's the skill I was talking about earlier of making sure this makes sense, not just going through motions, getting the answers, right? Yeah, that'll make a big difference. Okay, so why don't you guys try the last one? Okay, spoiler alert, it comes up to 12, but you're really practicing on this right here, so that your work at the end of it looks like this. It's neat, it's clear, it's vertical, right? It has an answer, it has units on the end, right? So, because really, we're just finding slope, but we're being very careful to write it certain ways so that when we start jumping these things up to something way more complicated than 3t squared, you have the structure to plug in any type of equation and it's going to work really well. I know it's tempting to look at it and say, I don't need to do all this to get 18. Resist that. It'll reward you in time. Okay. As I said, it will come up to 12. So I'll let you write that out.
Are you gonna be here after school tomorrow or no?